Hi, it's nice to see so many of you join our SELTECH virtual event. So let's start with our webinar. So Giulio, what's the plan for today?
Hi Mariam. Hi everyone. Yes, today we will have our partner and friends from AZOTEQ showing all the technical advantages of AZOTEQ inductive sensor and how we can apply them as an innovative user interface. In this webinar, AZOTEQ will show you several new applications in inductive sensing and how it can improve the current user interface solution. Yes, now we will leave Paris and go to the wonderful city of Cape Town where AZOTEQ is based. So take a nice cup of coffee, relax, not too much, and enjoy this webinar. But remember, stay safe. Hi Jean, thanks for taking the time to share your knowledge with us. So now the platform is yours.
Hey Julio, hey everyone. Nice to talk to you guys. Yeah, we are happy and lucky to be in Cape Town. It's Southern Hemisphere and we are heading into a lovely summer. So yeah, I hope everyone's keeping well. I see from the attendance list some of my old customers, some familiar names, some new names. So welcome to the webinar today. The topic is inductive sensing as a novel user interface. If you are from an engineering background, you probably would have heard of inductive sensing. It is not a new technology. It is something that is old, tried and tested, especially in automotive and industrial applications. But as you know, in automotive or industrial, the inductive sensors have always been bulky, they are big, they have a high power consumption. And AZOTEQ is really the first semiconductor design house to mature inductive sensing and miniaturize it and bring the power consumption down to a level where it is very suitable for consumer type applications. We have a very low power consumption. The parts are small, the sensing circuits are small, and we are cost effective compared to other input methods. So the webinar of today, the topic is how to use and some novel ideas around utilizing inductive sensing as a user interface. I will go relatively quick. There's a lot of topics and ideas to touch on. So the purpose is certainly not to go in depth, but just to touch and open your mind and create some ideas and stir some interest on novel ways to use the inductive sensing. And of course, afterwards, if there's questions either inside the webinar or outside of the webinar, we can go into a deeper dive. But I have at least between 15 and 20 concepts to share in the 40 to 50 minutes that we have available. So excuse me if I go quick, but I want to share the concepts and at least just open your mind of what can be done with inductive sensing. Let me switch to my presentation. All right, if somebody from the audience, maybe Mariki or Julia, if you can just give me a thumbs up, maybe on Skype or somewhere. I just want to make sure that my screen is actually in presenter mode before starting. So if I can just get an indication. All right, Savannah says everything's working fine. So let's start. Inductive sensing is based on a very simple principle where we excite an electromagnetic field around a coil, and that can be either self-induced or mutually induced from one coil to another. And should any conductive material disturb that electric field, the inductance in the coil will change. And if there is a change of inductance in the coil, then we know from the sensing IC side that some metal object or some conductive object move into the vicinity of the electric field. Now, if we use this moving metal part or the moving conductive part, we can use it as a switch, either something that is clicking like a metal dome, something that is sliding past it, something that is rotating past it, or even a very small minute deflection like 2 micron or 5 micron of movements we can detect with this inductive concept. So the inductive sensing can measure a very small change of movement. It is a linear movement in the vicinity of the electric field. It is a very simple circuit. Depending on self-inductance or mutual inductance, you either need 2 pins or you need 3 pins to the IC, and you need a coil. The coil can be either a trace on the PCB or it can be a surface mount component. And then the user interface is the human need to cause some kind of disturbance in the vicinity of this electric field. And this is normally by either pressing a button or moving a slider or applying a force to some sort of user interface area. The major advantage of inductive sensing, and I go back to the automotive and the industrial example, is the fact that it is a non-contact sensing method. Now you can see if you don't need to make electrical contact between the moving part, which is on the user interface side, and the electronics, you can make a completely waterproof and contactless sensing method. Now, if your electronics can be made waterproof, it holds a lot of advantages. Firstly, on the design side. Secondly, on the mechanical design, the mechanical housing, it simplifies the construction. And ultimately, it makes your application more reliable and more robust, since you don't have to worry about membranes that are wearing out, membranes that are cracking and allowing water in, or otherwise corrosion to the contact points. It is a purely contactless method with all the inherent reliability that you will find in industrial applications. Electronics can be fully sealed. Mechanics, very simple. If you look at some kind of housing, especially something that will be a tubular construction or so, that is very hard to assemble. Now you don't need to make any apertures or holes in this construction anymore. It can be a solid piece of plastics, electronics inside, and the moving parts on the outside. The inductive sensing is, of course, perfect for metal kind of user interfaces, and the construction becomes even simpler in this case because you can use the metal keycap can be used as the target material that is needed to cause this inductive disturbance that we are sensing. Another advantage over something like Hall effect sensing, for example, is the fact that the IC can be placed remotely from the sensing location. If you look at Hall effect sensors, the IC need to be populated or placed exactly in the same area where the moving magnet will be. In the case of inductive sensing, the IC can be in one location, and you can make your coils in remote locations distributed throughout the PCB. So a major advantage over Hall effect sensing. This, of course, also allows that multiple inductive keys can be sensed from a single IC. Comparing to Hall effect sensing again, if you want to do 4 Hall effect keys, you need 4 Hall effect sensing ICs. Whereas with the inductive sensing, a single IC can drive 4 coils and thereby sense 4 keys. In terms of the construction, I have an example on the screen here. This is a typical Bluetooth earbud that is becoming very popular recently. You will see on the left-hand picture with the black housing that we have a PCB with the trace in a gold color, the inductive coil indicated in a gold color. That is inside the housing. And then on the outside of the housing, you need to put the moving part for the user interface. In this instance, it is a familiar tactile button with a metal dome underneath. But different to an electromechanical switch, this dome switch does not need to make contact to the coil. We merely measure the instantaneous snap or collapse of the coil that is causing a change of inductance in the electric field, and we can measure that change of inductance. So a pure contactless metal dome is sensed by the coil on the opposite side of the housing. So automatically the advantages for waterproofing is apparent here. The housing can be sonically welded or glued, closed, fully hermetically sealed. The moving part on the outside can be exposed to water or dirt or dust or corrosion, and it will not have any detrimental effect on the performance of the inductive sensing. This just a small animation to show how a button like this can be constructed. We made an exploded view so that the parts are more clearly visible. Coil on the inside, moving parts on the outside, and the housing can be either glued or sonically welded together. What would be the applications for these buttons? First of all, true wireless stereo or Bluetooth earbuds. They all have the need for a very low profile key that needs to be waterproof. So you've seen from the previous animation that this can be very easily achieved. Also, the electronics can be located in a remote location from the tactile button. So space constraints can be easily overcome by placing the IC in a space in the Bluetooth where there's more space inside the housing, but not necessarily a good place to put a switch. Something like action cameras. This is an area, action cameras or any other outdoor electronic equipment. All of them need some kind of user interface, and you want the buttons to be reliable and fully waterproof. From the original animation, you can see that it is a very simple construction to achieve these waterproof buttons in something like an action camera. The third idea are watches or wearables. Again, something like a watch that need to be qualified to go to depths of 200 meters or such. It is a very complex, bulky, big, and expensive construction to make the buttons. And the buttons are often the first place where the water gets in, either due to aging or pressure-related issues. So once again, with the hermetically sealed housing, you overcome a lot of design constraints, you simplify the construction, and the simplified construction means a lower assembly cost and a higher reliability. Personal care products. I think all of you at one stage or the other have had typically a 200 euro electric toothbrush, and after 18 months you find that the membrane switch failed. So it is a 10-cent part that failed on your toothbrush, rendering the toothbrush useless. purely because of a cheap switch that was not reliable over time. So the inductive sensing is something that's very suitable for personal care products, especially products that are used in the shower or in the bathroom. Then in the kitchen, everyone is aware that there's always water splashing in the kitchen. So you want waterproof interfaces. The capacitive sensing is an alternative where you can have a pure touch interface. But in many instances, either from an industrial design perspective or from a usability perspective, the user would still prefer tactile buttons. And then this inductive sensing is a very suitable method. It can be easily cleaned. In this instance, it's a vertical surface, but you can imagine in a horizontal surface, it's very easy for water to get into conventional switches. So with the inductive approach, again, you can seal your electronics from all of the moving parts. It's also very clean to wash. You can even submerge user interface areas now, which previously was not possible to submerge it, either to put it in a washing basin or in a dishwasher. For outdoor applications, inductive sensing makes a lot of sense. Firstly, because we support metal surfaces. So in the instance that I show on my screen, again, the keycap can simply be used as the inductive target that is sensed. Inherently, these products are more vandal-proof and very easy to make them waterproof compared to conventional switches. Then, if we look at the subset of the inductive sensing, the switches that I've shown in the first section of my presentation were all replacements for conventional tactile switches, where the user expects an instantaneous click feeling. But there's certainly other applications where force that is applied to the user interface is a more intuitive or a more acceptable user interface. Take, for example, Bluetooth earbuds. In most instances, you don't want a tactile button on your Bluetooth earbud because you don't want to press the earbud down your ear canal. And users don't like the audio click sound that the tactile button makes. So that is why some of the leading TWS brands are using a force sensing technique where you will squeeze the earbud between your index finger and your thumb. Now the inductive sensing is very suitable for force sensing as well. Whereas before we measured the instantaneous click of the metal dome, for force sensing, we measure minute deflections of the metal target. The example that I have on the screen is the stem of a Bluetooth earbud. Maybe many of you would be familiar with something like the Huawei earbuds or the Apple AirPods, which have the small microphone boom. This is a very suitable user interface to squeeze between your thumb and your forefinger. So what we are proposing on the screen here is a spring-like structure that is hovering over the coil. Now, if you apply a small force to the outside of the stem, that spring structure will move closer to the coil, and we can measure that minute deflection. We can measure with the inductive sensing technique. I have a graph here that shows the amount of deflection or displacement on the x-axis compared to the counts, the raw sensor counts. or you can also translate it to a certain force. So you can see as low as 5 micrometers, we are already detecting the first movements of the pressure that is applied. And the more pressure that is applied, we get a very linear signal in the working range. So from 0 micron all the way up to 60 micron, we get a very linear response from the inductive sensor. So this is a technique, a tool, sensing IC to measure very small deflections at a significantly lower power consumption that you would have needed otherwise for a technology like a strain gauge or such. On the screen is just an alternative idea to measure the force sensing. So in this instance, the force is applied in the Z direction, and we have the metal target kept in position by spring foam type material, and we measure that small deflection with the inductive coil. So force sensing, very suitable for any kind of user interfaces where you don't want an acoustic sound from the tactile button, or you don't want that instantaneous click feeling, or where the user interface is something that you will squeeze between index finger and thumb, or otherwise where you want to detect some kind of linear movement in a certain working range. As I showed before, from 5 all the way up to 60, it depends on your working range. You can design it to be more sensitive in the early travel, or have a higher dynamic range to reach up to 200 micron or so. The third idea or application for the inductive sensing is to make a slider. Now, if you ever tried to make a waterproof slider interface, that is significantly more cumbersome and challenging than making a button waterproof. Again, with the inductive sensing, it can be a very simple construction. You need to place coils, and the amount of coils and the size of the coils will depend on how much precision and how much resolution you require. But typically, you will design the coils underneath the travel direction of a metal target. So again, making this waterproof is very easy because the moving part can move in a slot that is on the opposite side of a sealed housing with the electronics all inside, sealed inside. I have a small animation here. This is just one of AZOTEQ's demo kits. This is available on request. It is a demo kit showing 40 millimeter of travel with 1 millimeter of accuracy. So you see the advantages. The slider can be exposed to the outside. Water, dust, dirt can get in, but the electronics are sealed from the inside and no physical contact required. So sliders and buttons, again, very useful in kitchen appliances. The example that I have on the screen is a solid housing molded in a 1-step or a 2-step process where the a metal foil or a metal string can be mounted or molded on the inside, and the deflection of the housing on the outside is measured by the inductive method on the inside. Take, for example, something like a vending machine. 2 or 3 ideas to use the inductive sensing in a vending machine. First and foremost, we can make a very nice vandal-proof user interface on the buttons. But then to detect the tray position, typically the tray needs to travel over a distance even as much as 600 or 700 millimeters. If you want to design a slider with 700 millimeters of travel with Hall effect sensors, typically you will need to put down 20 or more Hall effect ICs. Whereas with the AZOTEQ solution, we have single chip solutions that can drive anything up to 8 inductive coils. So you can distribute your coils along the travel of the stay of the tray. So the examples that we've done before is that the 700 or 800 millimeters of travel can typically be done with 3 ICs and with a precision as low as 1 centimeter, between 1 and 2 centimeter for the tray detection. Of course, the inductive sensing very suitable for any kind of tamper detection as well. If any metal object is forced either into the payment slot or the money return slot or the user interface, easy to detect metal objects that's used as a tamper or something to break it open with the inductive method. Lastly, something that is even more important than slider interfaces, but even more harder to implement in waterproof applications and in contactless applications is rotary sensing. So much the same as we discussed before with the linear slider, where we can detect the movement of a metal target along a linear track. You can design your coils in a circular fashion and then have your metal target rotate in close vicinity to these coils. So the animation on the screen is again one of the AZOTEQ demo kits. This is a 50 millimeter diameter knob, something that is typical for washing machines, laundromats, dishwashers as a user interface. You can design the coils behind the front panel and then have the moving part on the outside, and no need for a shaft or any special O-rings or any parts required for sealing the moving part off from the electronics. The demo kit in the animation is something with a 16 position precision that is working through 4 millimeters of glass. Right now we are also working on models with 32 positions on in the 360 degree of travel, also working behind anything 4 millimeter plastic or even 4 millimeter thick glass. This is just an alternative idea. So the application for rotary sensing, again, kitchen appliances where you need to have splash-proof, waterproof user interfaces, vertical surfaces like a blender, but even more important is horizontal surfaces, something like a stovetop. Imagine my animation from before. You can have a solid piece of glass, Gorilla Glass, over your stovetop, and the knob can only needs to be located in a small recess or be kept in position with the magnetic method. So the knob is completely contactless from the underlying electronics, with the major advantage that any spillage will not get into your electronics, especially if the material that is boiling over is hot and sticky. We can have a very nice rotating user interface, because let's face it, our customers are familiar to the rotation interfaces. They like the knob, but it is a headache for the engineers to design the knob. Another derivative of the rotation sensing is to do speed sensing. Let's say you need to measure the flow in a pipe or something like that, then the inductive sensing is a very nice non-obtrusive method. It is something that can be applied afterwards or retrofitted if you have a moving metal part inside the pipe or whatever the rotating mechanism is. We need to get a inductive sensing coil in close vicinity to that rotating part, and then it's very easy for us by counting the pulses to derive the speed of the rotating part. Then the last idea, if we are looking again to consumer devices, this in particular is an example for a gaming console controller. This is a popular user interface in the gaming space where you want a trigger button. Typically, this technology today is done by rotating a rheostat, and those rheostats are notoriously easy to fail in the short lifetime. The points get corroded or the carbon gets worn off from the points. So again, with the contactless inductive method, we can have high precision. This particular example on the screen is something with 265 positions, purely contactless. So basically, infinite lifetime on something like a trigger button that could not be otherwise achieved by a rheostat. So gaming buttons, typically the trigger buttons. To a lesser extent, we can probably use it for the joysticks, definitely for the conventional buttons, but very applicable for the trigger up to 8-bit position encoder, completely contactless. I'm getting towards the end of my presentation. One more idea in the security and home automation space is to use the inductive sensing as a door and window monitor. The idea that we are proposing on the screen here is to have a small point cell sized module that is easy to retrofit to your door. In this instance, if the door frame is made from a metal or an aluminum material, you simply use the door frame as your target material, or otherwise, if you have a non-conductive like a polycarbonate or a wooden frame, just apply a small metal foil or metal part to the door frame that you can use as the contact sensor. So again, something very simple, very robust, it's waterproof, and it's also tamper-proof. Today, most of these contact sensors in the home automation and security space are reed relays, which are very easily fooled by magnets. The inductive sensing will not be fooled by a magnet and cannot be overridden by a magnet. All right, ladies and gentlemen, I think that's it from my side. If there's any questions, we have time available for a Q&A session. So yeah, Savannah, I guess if you can control the microphones from the audience, then we can open the floor for any questions.
Hello, Jean. This is Uwe speaking.
Hey, Uwe. Good morning.
Good morning. Could you iterate how small the current consumption of a battery-powered inductive sensor could be, like for the door lock? Well, typically there is a coin cell or something like that to power it.
Yeah. Uwe, the power consumption is a direct function of the sampling frequency. So typically, in a user interface, we would want to sample relatively fast, between 10 and 20 microseconds, to give a nice and responsive user interface. But in the instance of something like a security application, where you don't particularly need to know within 10 milliseconds that the door is opened, 100 millisecond, 250 millisecond, even 1 second is good enough. Then we can drive the power consumption down to as low as about 3 microamperes. So 3 or 4 microamperes, sampling at as low frequency like 4 hertz or 2 hertz.
Thank you very much.
Anybody else? Uwe, do you have a specific application for the contact sensor?
That was really about the door lock and window open-close detection, kind of.
Okay.
Yes, and maybe interesting also for the audience to understand how low it can go.
Yeah.
So it's very impressive low current consumption, which allows from a small battery cell to run such a device for several years.
Exactly. Yeah. I think it's probably good to add at this point the focus of the webinar is really the inductive sensing, but for our audience familiar with AZOTEQ's offering, they will know that we have the Prox Fusion approach, whereby we integrate multiple sensors into a same IC. So inductive sensing is just one of the sensing methods. So you can imagine with the small module that I have on the screen, if you employ the capacitive sensing alongside with the inductive sensing, then you can use the capacitive sensing either for a level of tamper detection or another level of contact detection. So you can have a capacitive method as well as an inductive method, which now makes it almost impossible to tamper and override the sensor. Either the capacitive or the inductive is going to trip one way or the other. So this is vastly more robust and secure compared to conventional read relays, where my kid that is 6 years old can override the read relay that is used as my contact sensor from my alarm system in the house.
You showed also the door entry panel with inductive keys, which is very easily electrically sealed and very nice, waterproof, and there is no issue with raindrops and water and whatsoever. So I think that's a great technology to overcome that hurdle and challenge that's there with capacitive. And you have the tactile feeling on top, which many people like, especially elderly, appreciate that there is something to move. For like a 12 key panel where you have the numbers plus some function keys, which are very typical. How many ICs are needed, or what's the best approach there? And maybe also considering a proximity function on top, so having a kind of small antenna around to say, okay, I approach, light up the display in the dark, I can see the panel and press the correct numbers. What's the right way to approach this?
So you are very right. I think you hit on a few important points. The capacitive sensing is a popular, touch sensing is a popular and a very elegant user interface, very suitable for inside the house, very suitable for tech savvy users. So I like the fact that you mentioned for older people, they still like a tactile button. And it is the same for the user of the point of sale paying with his credit card machine. You want to be very sure that you press the button. Now with something elegant like a touch interface, if there's an audio feedback or a screen behind, then it's easy to give some kind of feedback that the button was pressed. But often, like the door intercom system, when you are outside on the street and it is noisy and maybe it is rainy or the sun is shining on the screen, you can't see the screen or you can't hear the audio feedback. So you want that tactile feeling, the fact that you press something. So the inductive sensing, typically with the dome that I indicated, there are other mechanical ways to make it. The dome is just something that people are familiar with. So the dome gives you the tactile feedback, whereas at the same time giving you that instantaneous snap, so it feels like a button that you pressed, but we don't need the electrical contact as with a conventional switch. So that's the nice thing. The dome can corrode, or the dome can be exposed to dust and dirt and water. It will not impact on the performance. In terms of ICs needed, today from our existing portfolio, we can do up to 4 coils with a single IC. So for the 12 keys, with the existing portfolio, you will need up to 3 ICs, but we have a roadmap towards the end of next year. We have ICs coming out that can do up to 15 coils from a single IC. So very soon, the whole 12 key keypad will be able to support that with a single IC from AZOTEQ. For proximity sensing, I think we will probably revert to capacitive sensing. The advantage with the capacitive sensing is that it's a very omnidirectional detection method. And in the case of the intercom system, if you just use the proximity sensing to trigger a backlighting or something like that, then we are not too worried about false detections. You do not want a false positive on your keypad, but if it's just the backlighting that is accidentally triggered, let's say by rain or something like that, it's not that critical. The big advantage of proximity sensing is that it comes for free. The capacitive sensing is already embedded inside the inductive sensing ICs, so you just need to put a small trace on the PCB. Sacrifice one of the sensing channels for capacitive sensing, and you have a nice backlighting that can trigger as the user is approaching it, but it's not staying on all the time, only when somebody is operating the keypad.
Thanks very much.
Hi, Sean.
Yep.
Can you hear me?
Go ahead.
Yeah.
Go ahead.
Yeah,
yes, I can hear you. Go ahead.
Yes, great. I'm Kim from EPOS in Denmark. Yeah.
Hey, Kim. Nice to talk to you.
Yes, nice to talk to you. Thanks for the presentation.
You're welcome.
Yes, thank you. I have a question about the technique that you use to detect the change in the field that you detect that the button is pressed or not. So I can see from the presentation that you have some counting inside. You do some algorithm to count some kind of parameter during you scan it always, and when there's a metal object that push closer, there's a change in the distance from that metal object to your coil. That counting will be shipped up and down. So can you tell me what exactly is that? What that parameter is counting, and is this are you like pumping some sensing current, or is it voltage, or talking about the technique or algorithm to detect the change, please? Yes.
Yeah. Kim, we are measuring a derivative of the inductance. So in its purest form, we are measuring a change of current flowing through the coil. So if the inductance of the coil is changed, then the amount of current flowing through the coil will change. So we are measuring a change in current through the coil, and from that we derive that the inductance of the coil have changed. So from my picture on the screen, I think my screen is sharing again. You see there's a metal spring hovering over the coil.
Yeah.
So if you move that metal spring closer to the coil, it is disturbing the electric field around the coil. That disturbance of the field is causing a change of inductance of the coil. And when the inductance of the coil changes, the current flowing through the coil changes, and we measure that. It's not a pure A to D technique, but it is a technique that is similar to an analog to digital converter.
Yeah, I see. So in order to detect that change in the current, I guess that you are sending a chain of pulse with a fixed width, and then that voltage applied to the inductor, and you measure the current. And if the inductor is at the default value, it will measure a specific value of current. And once the button is pushed, and then you have a change in the inductance, and since the chain of pulse voltage is fixed, then you will see a change in the current because of the change in the inductance. So then with the change in current you detect, and you know that the button has been pushed, or the force sensor has been squeezed. And
exactly. And that train of pulses, you referred to a train of pulses. So if there's no activation, for every sample, the change of pulse, the amount of pulses would be the same. Let's say a number of 500. So let's say every time it's 500. But then when the button is pressed, maybe only 300 of those pulses in the sample. And that is the way how we set up the threshold. So you can adjust the threshold to be more sensitive or less sensitive, or even something linear like I have on the screen right now. Just maybe one more point while I have this on the screen is the advantage of this force sensing, especially in this true wireless application over capacitive sensing. If you were to use a capacitive sensing for this force sensor, then water would also interfere with the capacitive sensor. So you can get false positives from water interference. Even if no force is applied, water will still cause a capacitive disturbance to the electronics inside. And that is why the inductive sensing is such an elegant technique. And that is why it's been used in industry for 50 or 60 years already. Water and other interferences does not influence it. So a very nice and a robust user interface. If you have to use it, in this instance, it's something that is used outdoors, that is used in the rain. So a very suitable interface for something that is used outdoors in the rain. And the other big advantage, gloves. If you are using gloves either because you are cycling or you are in cold temperatures, then the force sensing is a nice user interface, where gloves and capacitive sensing, it is always tricky to get that right. If you tune it too sensitive, then it works with thick gloves, but you can get false activations. If you don't tune it sensitive enough, then the thick gloves are not working. So
yeah, I see. Yeah, with capacitive sensing, then it depends a lot on the material outside and the environment. So if it's raining, or if you have that on a glass of water, it will may have a false triggering. and
Yeah.
different type of gloves, the thickness of the gloves also. Yeah, so there's a lot of things you have to tune. It works for capacity sensing. It works for certain materials, certain thickness, but then once it changes, and you might not have a reliable detection anymore.
Yeah. If you have a controlled environment, if you know what the environment is like, then capacitive sensing is a very elegant technique, and it has a lot of advantages. But when the environment is uncontrolled, like this through wireless, maybe you are in a hot bus and you step out into the cold street, or it's raining, or it's snow, or it's gloves. You don't know. There's too many unknown factors. Then the inductive sensing makes a lot of sense, over and above the advantages that it brings in terms of reliability.
Yeah, I got it. Thank you very much, John.
You're welcome. Anybody else? Any other questions?
This is Uwe again. Hi, John.
Hey, Uwe.
You just discussed those changes in environmental effects. Now, semiconductors have some trend to change a value with change of temperature, for example. Is that compensated for with all of the inductive, or are there specific versions? Can you comment on temperature drift compensation?
Okay. Uwe, there are three parts to my answer. The first part is the inductive sensing is less exposed to drift caused by temperature, so inherently it is a little more robust compared to capacitive. Secondly, what we can do, and we have done it for some of our customers, is to put down a reference channel. So let's take the picture that I have on the screen, for example. Let's say we have a large concern about the impact of either heat or cold on the user interface. We will put down a second coil that cannot be activated by the user. Okay, so this second coil, we put it down on the same material, but it cannot be influenced by the user. So now, when we see both coils, the reference one and the user interface coils, when we see both of them changing value, we know it's due to the environment. When we only see one of them changing value, then we know it's due to a user interaction. Okay, so I hope this is a clear explanation how we can use a reference channel to deduct that it is an environmental change and it is not a user interaction. And then the third part to the solution is all the new generation AZOTEQ ICs has an on-chip temperature sensor. In most instances, we don't open this temperature sensor to the users, but we rather use it for our internal algorithms to track changes in the baseline caused by temperature drift. So we also compensate on chip for any drift in baseline due to environmental changes. But the most popular one and the most controllable one is to use this reference channel. It is a very nice technique. You can even detect temperature shocks. Let's say you have a fitness tracker with a force sensing interface. You are sitting on a nice hot sunny day on the beach with your fitness tracker on your arm. The sun is shining. It is 40 degrees C. The next moment you jump into the cold water at 10 degrees C. That temperature shock can trigger a false activation on your user interface, but if you have this reference channel, the reference channel will also be influenced by this temperature shock, and we can ignore anything that we see on the user interface coil, for example.
Many thanks. That's excellent explanation, I think. So really, really good.
Thanks.
Yeah, thank you. Thank you very much.
Yeah.
Hi, John.
Hey, Kim, go ahead.
Yeah, I try to use the raising hand button here, but I don't know if I press it correctly. Can you see it?
Yeah, I see your hand.
Okay. So now my hand is raised.
Yeah.
Okay.
Go ahead, Kim.
Yeah. Thank you. I would like to ask you about like how difficult it is to determine the design of the coil. So like how large it is and how many turns and so on. Do you have a guideline for it? And normally how difficult it is to make it work for this inductive sensing? Because as in this solution, you have your IC, that you have the algorithm there that we can program different things, different parameter and threshold, but then the electronics outside is the inductor. So how difficult it is to make it work and to come up with a inductor size and turns, number of turns, and so on.
Yeah.
Just for the capacitive sensing, I know that designing an electrode can also be a challenge. So as for inductive sensing, I guess it is you have to face a problem of designing the coil, right? So can you comment on this?
Yeah, yeah, I understand your question.
Yes.
I think firstly the inductive sensing is more forgiving compared to capacitive sensing, so a little bit easier in that sense. Also, you can control the inductive fields are much better controlled since they are located in the area of the coil, whereas with the capacitive sensing, your whole sensing trace is exposed and often sensitive to interferences. So a little bit easier in that respect. To design your first and your second and your third design, perhaps, we can help you with that, either with reference designs. In terms of amount of coils and what the distance between the coils should be, we have application notes for that, or otherwise we can assign an engineer to either help you or review your design. And then there's normally a tuning capacitor. You want to get the coil to its resonant frequency, and so after you've made your PCB design, which you believe is the best you can, then it's a little bit of experimentation, trying 2 or 3 different capacitors to get your coil to the resonant frequency. So the first and the second time it takes a little bit of time, but by the third time it's relatively easy to make these, and then it's relatively easy to take them to mass production like that. So yeah, so Kim, you don't need to worry about it. It's not a black art. It's not any magic. It's relatively straightforward, using AZOTEQ's application notes and a little bit of engineering support just for your first or your second design.
That's very great to hear. So you also mentioned about choosing a capacitor to put a resonant frequency, correct resonant frequency on this inductive sensing. Did I hear it correctly?
Yes, it is performing. You want to get it as close as possible in the mutual inductance. You want to get it as close as possible to the resonant frequency where the 2 coils are resonating, and for that we use a external tuning capacitor.
External tuning capacitor. Okay.
Yeah, external component. Yeah. But that's just but the value of that capacitor is determined it's verified by design. So once you know the value of that capacitor for that specific layout on your PCB, then after that you can go to mass production with those values. With that particular PCB design and that capacitor value, you can go to mass production. It does not need to be tuned for every single unit that is produced.
Mm-hmm. So in a design for inductive sensing, how many coils do you have? Is this only one? Or
do you mean how many turns on the coil, or how many coils?
Not returns. How many coil?
Something like the 269, which is most widely used in true wireless. The IQS 269 supports 3 coils, and our new upcoming IC, the 7210, can support 4 coils from a single IC.
So let's say if you if an IC can support 3 coils, then 1 coil can be used for reference as a reference channel, and the other 2 coils can be used for 2 application of inductive sensing.
Yeah, that's correct. Yeah, two buttons typically.
2 buttons or 1 button. One.
Kim, yeah, there's not many instances where you will need the reference channel. So if you don't need the reference channel, you can use all 3 coils for the user interface. Mm-hmm. But like the example that I used, where you can go into the heat and maybe there's a temperature shock due to cold or whatever, then you need the reference coil.
Yeah,
I have a question from a gentleman called Eugene Zepko. Eugene, if you turn on your microphone, then the floor is yours. All right, Eugene, I see. Oh, all right. Ladies and gentlemen, there's a question from Eugene. I will read it out loud. He does not have audio, but he posted some questions in the question pane. Hello, John. What will be the power consumption for earbud, conductive button, and a 1mm slider? Will there be any measurable differences with a 10 to 50 millisecond response time? The power consumption, Eugene, maybe I can get back to you afterwards with more specifics from a data sheet, but I'm estimating in the 10 to 20 microampere range. But after the meeting, I will make sure that I share the correct data with you. Then Eugene has a second question, is to whether it's possible to measure humidity. Eugene, humidity, or we can detect a change of humidity with capacitive techniques, but humidity have very little influence on the inductive sensing. So the short answer is that inductive sensing is not a suitable measuring technique for humidity. So no. All right. Any other questions? Gutierre, I see your hand going up. So yeah,
yes.
Nice to see you here.
Hello, Jean. Thank you a lot for this presentation. It's interesting to observe what you can propose with your IC and solution. So thanks a lot first for that. My question will be 2 questions in fact. So what would be the EMC robustness for your IC solution? And the second question from my side is more or less related to the answer just provided. It's how fast can you go versus how much the power consumption will be.
Yeah. Gotcha. So in terms of EMC, we are at this moment busy with the design for the user interface on a dishwasher which are white goods. I don't have the numbers offhand, but typically the white goods requirement are much more stringent than consumer goods where you guys are playing. So again, afterwards I can share specifics with you, but you will be fine. For consumer goods, you will be fine. There should not be any issues.
Okay.
On your second question, how fast you can go, we have a customer in, or let's say another customer also in the gaming arena where they require a 1 millisecond response time. So we can sample and generate the interrupt within 1 millisecond. Of course, the power consumption is much higher then if you require the 1 millisecond response time, but that is the fastest that we can go. It's below 1 millisecond.
Okay, perfect. Okay, thank you.
Gutierre, if you have a specific example of how fast you want to sample, as well as what precision you require for something like I have on the screen, for the force sensing, we require a very high precision. So the target counts will be high. It takes longer to take the sample, so inherently higher power consumption when you want very high precision. And the same when you have a very high sampling frequency, the power consumption will also go up. But if you can get away with either less precision or with a lower sampling frequency, then the power consumption goes down again. So you are welcome to share a specific example or a specific application with us, and we can give you an estimate what the power consumption would be.
For sure, still appreciate your support. One minor question behind that is also, for sure, your IC always integrate serial communication line. Are you able also to provide some IC without this serial communication line, just transmit analog value to the MCU?
Gutierre, the analog values are not open to our customers at the moment. Okay. You can get access to the count value. You are familiar with our sensing technique where we have this this charge transfer technique. So you can read the raw count values can be read from the registers, but not an analog value. No.
Okay, perfect. Thank you. Thank you.
You're welcome. Kim, you have your hand up once again. Go ahead.
Yes, John. So we at our company we are pre-investigating the use of capacitive sensing and inductive sensing. So I am interested in this application notes that you mentioned. So we are already discussing with SELTECH, but we haven't kickstarted the collaboration yet. So I wonder if at what phase are you willing to share the application note? Is this you want to wait until we start a collaboration, or can the application note be shared earlier right now so that we can do some pre-study on that to understand better?
No, of course, Kim, if the NDA is in place, as long as the NDA is in place, we can share the application note. So
okay.
If your SELTECH interface can maybe just take an action item to follow up afterwards. I don't recall offhand whether our NDA is in place, but after that, sure, we can share it. Mm-hmm. And Kim, we are also very happy to open a application engineer contact window to you. for specific questions or specific experiments. The
Mhm.
inductive sensing, it's a new technique in the consumer space. We understand that we need to educate our customers to some extent, and it's part of our offering. So we are very happy to hold your hand in the early days. I heard earlier you are concerned about designing the coil and getting it right. We are more than prepared to hold your hand until you have gained the necessary experience.
Yeah, that's super. Yeah, we will look into that NDA when and how when is the right time to do. Yeah.
All right.
I will
But
get back.
you're welcome. But the offer stands.
Mm-hmm. Yeah. Yes. Thank you. That's my question.
Right. Right. I had another question coming from Eugene. Eugene is asking for some more detailed information around the power consumption. I raise it here because I think it's relevant for everybody in the meeting. It doesn't matter about your specific application. We are very happy to calculate or to estimate the power consumption if you give us your application, the speed of the sampling, the precision that you required. As I said earlier to Gautier, it is the higher precision or the higher frequency will have an impact on the power consumption. So once we understand your application, we can agree the sensing precision, and based on that we can give you an estimate on the power consumption. So yeah, Eugene, send us your example application and we can estimate the power consumption for you based on that. Any other questions or any specific slide that you would want me to go back to? Maybe spend a little bit more time or more explanation on any specific slide that I showed before? Kim, go ahead. All right, I think if there's no more questions, we can stop the webinar. Everybody, thank you for joining. Thank you for listening. I hope it was informative. As I said in the beginning, I just touched 20 ideas in 30 minutes, not so easy to convey it. So I just wanted to touch on all the various ideas. But of course, reach out to your SELTECH contact window. SELTECH has a very good first line of response. And if we need to go into a deeper dive, either reach out to us directly with SELTECH and CC, or ask SELTECH to reach out to AZOTEQ. We can make a deeper dive into any specific questions that you have, whether it's on the electronics or the tuning circuit or the PCB layout or the power consumption. We are very happy to help and educate you. But I think finally, in closing, from AZOTEQ's side, we believe the inductive sensing holds just as much promise as capacitive sensing held 10 or 15 years ago. It opened up a lot of new opportunities. The capacitive sensing opened up new opportunities, but the application for inductive sensing or the advantages around inductive sensing is just so much more than the capacitive sensing. So personally, we are very excited. We have our roadmap is aligned such that we support all these different inductive input techniques, and we truly believe that in the coming years it will be very valuable user interface sensing technique. Thank you, everyone. All right. I have a question from a gentleman. Would this technology work if there are magnets close by or a motor? Yes, sir, it can. Of course, if the motor is generating very high levels of EMC, we need to design for that on a PCB level. But the short answer is yes. We can make it work in and around high levels of EMC. My next question is, how small can an inductive button be for a small size wearable? Sir, we can, if you put the coil on the PCB, typically we would need a coil of diameter of 3 or 4 millimeters. That is putting the coil on the PCB, in which instance your sensing circuit is in essence for free. But otherwise, we've done concepts where we use a small surface mount component. So that literally consumes a space of less than 1 millimeter by 1 millimeter on your PCB. Then your conductive coil is turned in the Z direction, and that consumes extremely little board space. So very suitable for a wearable. Talking about the wearables, the inductive sensing makes a lot of sense in a wearable. It is one of those applications where you don't know whether the user are going to be using gloves or not. Maybe he's running, maybe he needs to swim. So all the advantages that I discussed, so very, very applicable in the wearable space. The next question in your example of removable stove knob, how do you detect and recognize the right kitchen stove knob is being put back afterwards? And then the gentleman gives an example by a specific weld pattern on the knob, perhaps. Yes, sir. We can either, in my example, the metal foil on the knob was completely symmetrical. So we can design it unsymmetrical, that there's some kind of binary code embedded there. So something like that can be done. I have a question from one of our sales representatives asking how soon this presentation would be available to share with customers. Sir, you can reach out directly to SELTECH, who were the organizers of this webinar. They will share it with you as soon as they can, but there's nothing holding us back. All the information in here is in the public domain. So we are happy to share it with you, and you can share it with your customers. My next question from the floor. Can the inductive have the same feel as capacitive sensing? The inductive sensing is based on the principle that there needs to be a small amount of movement or deflection in order to change the inductance on a coil. So you need to apply a very little bit of force. The force is a function of the stiffness of the housing, but AZOTEQ typically needs to detect 2 micrometer or more of movement. So whereas capacitive sensing do not require any deflection of the top surface, the inductive sensing do require a small amount of deflection. But if you are employing it in something like the plastic housing, or you have a plastic front cover, the perceived pressure from the user can be such that it feels the same as capacitive, even though there's a small amount of deflection behind it. I have a question whether the slider function can be implemented on a wearable. The answer to that question is twofold. If you can have a mechanical part that physically moves, you can realize a very high precision slider. let's say in the case I'm thinking of my digital camera, for example. It has a small door that opens. Often remote controls have a small section that slides. So if you have a physical part that can slide, you can realize a very high precision, to even 0.5 millimeters of precision. If there is no moving part and the user literally has to cause a deflection in the top cover as he is sliding, then the precision will be significantly reduced and it becomes a function of the stiffness of the housing. But sure, we can still do the slider and it will still be applicable for something where you just want to use the sliding function, let's say to unlock the screen or something simple like that, where you don't need the high precision of the mechanical part moving. I'm just going to turn off my camera quickly. I'm having a hard time navigating between the question screen and anybody that would like to raise their hands. Ladies and gentlemen, you are welcome to use the audio interface as well. I'm still not sure if my audio is working on my side. Maybe somebody from SELTECH can just make a test. I don't see anybody's microphones going on. All right, any more questions? All right, I have a comment here that the unmute doesn't work. Savannah, if you are still...
It's working now, John.
All right, now it's working. All right, I have a question from the floor. Go ahead, sir. You can go ahead. I had a question.
Sorry, I did not have a question. I was just pointing out that the mute was working, or that it was unmuted.
All right, thank you. All right, another question from the floor. How about calibration? Is it done during manufacturing? The design is calibrated during the design phase. So we follow a procedure where we say it is verified by design. So the IC, once it's properly designed and the correct thresholds have been selected during the design phase, those thresholds can be used throughout the lifetime of the device. The device will perform a small auto calibration routine every time at power up, but it basically remains calibrated for life. In the instance of a high precision slider, either that or the trigger button, for that you would typically need a calibration step only once during manufacturing, and then it remains calibrated. But for a simple button input, no calibration is required. I have a question on the trigger button, the amount of resolution that can be obtained. So we can achieve down to 0.5 millimeter of precision. So it is a function of the amount of travel that you have. Typically, the gaming consoles require 8 bits of resolution, and we can easily achieve the 256 positions. Another question from the floor, whether a Linux kernel driver is available. Yes, we do. For all the newest devices on the website, there are links. It's either sample code developed by AZOTEQ, or we have some third-party guys developing the code, but sure, sample drivers are available for all the recent devices. All right, next question. Does it go into a low power mode after a period of inactivity to save power? Yes, you can set up the device for the sampling frequency, both during active mode as well as low power mode. So typically, power architecture would be, while the user is interacting with the keys, you want a very quick response. So typically we would be sampling at 10 milliseconds or so. After a certain period of non-activity, let's say 5 seconds or 10 seconds, then we can go into a low power mode where we sample at a reduced frequency, either 100 Hertz or 25 Hertz, depending on what your requirement is, how quick it should wake up. So sampling at this low rate, 10 Hertz or 4 Hertz, we can drive the power consumption down on a single key, probably as low as 4 or 5 microamp in this low power mode. But that is fully configurable over the I2C interface. You set up a register the way you would want your power architecture to work. How soon to wake up, how soon to go to sleep. Any other questions, or if anybody would like me to go back to a specific slide and maybe do a slightly deeper dive on a specific concept, I'm very happy to do that. Ladies and gentlemen, this presentation will be available from SELTECH shortly after the webinar. From AZOTEQ and our partner SELTECH side, we are happy to engage outside of this webinar on a deeper dive. If you have a specific application in mind and you have specific questions around that, whether it's on the PCB layout or the power consumption or the mechanical construction, we're very happy to engage with you and do a bit of a deeper dive. I have a new question from the floor. How many inductive sensors can be designed on a single IC? So we have single channel devices, then some devices can do 3 channels, and then the biggest one at the moment in our portfolio is a 4 channel inductive sensing device. On the roadmap, probably a year out or so, we will go up to 15 keys from a single IC, but today either 3 or 4 inductive keys from a single IC. Another question in, the gentleman is asking for a bit more information about capacitive sensing as opposed to inductive sensing for wearable applications. Sir, AZOTEQ actually has a very long legacy in capacitive sensing, and specifically we have a very good position in wearables. So it's probably best that we engage outside of this webinar. We have a very wide variety of solutions for capacitive sensing, whether it be on the user interface side or wear detection or a combination of applications. So please reach out either to AZOTEQ or SELTECH directly after the webinar. The purpose today was really to open your mind and share some ideas about the inductive user interface. But it doesn't mean that this is the only thing that AZOTEQ is doing. So we're happy to engage with you on a deeper dive for capacitive solutions in the wearable spaces. Another question in the type of user interfaces available for the inductive sensing IC. The popular and most frequent interface would be I2C. The benefit of the I2C is that you, on the one hand, you have access to raw information on the IC. If you need more than just the single bit indicating that the threshold was exceeded, you can get access to the raw data over the I2C interface. Otherwise, you are able to adjust certain parameters on the fly. Let's say you want to adjust a threshold or sampling frequency or something like that. You have the ability over the I2C interface. For the applications where the master controller do not have an I2C interface, we have a device that will be released to market during December of this year called the IQS 630. And this is a single channel inductive sensing IC that has a GPIO interface.
So thanks, Jean. I don't know if you still have questions.
I have one more question, Julio, that came in. It's one of our attendees asking whether we have an evaluation board. Sure, you can look at the IQS 269 evaluation board, or otherwise drop us an email. Let us know your application. If you're looking for something very specific like the SUIDER or something like that, let us know your application, and we will support you either with a standard board or otherwise with a little bit of customization. We're happy to do that.
So yeah, so perfect. Thanks, Jean. Yeah, it was really interesting. You shared a lot of inputs, information, ideas. I hope everyone enjoyed this time. Thank you again. And if there is no more question, then remind to address all your inputs to your sales channel that you have and locally. And thank you, and stay safe again. Bye.
All right, everyone. Thank you for attending to SELTECH. Thank you for arranging the webinar. Yeah, I can just say from AZOTEC's side, we are truly excited about this inductive sensing user interface. It holds a lot of promise, and like I said right in the beginning, the fact that this is widely adopted in the automotive and the industrial space, it just shows that the inherent advantages in terms of reliability and robustness is there. We have now positioned it such that it is very friendly in the consumer space. So now it remains for our customers to adopt it and really to unlock all the advantages that comes with the inductive sensing.
So perfect. I think the message was clear. Thank you again.
You're welcome. Thank you for arranging it. Thank you everyone for attending. Julio, I don't know, do you want to announce how you will distribute the, would you like attendees to request the presentation, or will you send it out to the list?
Yes, they will be available, the presentation, within the end of the week. As the virtual event will end, we will share all these webinars so that the people attending, they can get this material. And in any case, don't hesitate to ask for more information. Like you mentioned, we have there are demos available, there are other application and samples. Just don't hesitate to ask for. Perfect. So thank you, everyone. Then I wish you a nice rest of the day and stay safe.
Thank you. Thank you, everyone. Bye-bye. It was nice talking to you. Bye-bye.
Bye.